I've updated several things in the Stat 512. Schedule of courses. The schedule, I mean, sorry. So if you take a look, first of all, I posted Chapter 13, the assignment. If you look at the schedule, I'm pretty sure I'm right about that final exam. It's on the 12th at 11 a.m. till 1 p.m. And so I'm making, this Chapter 13 assignment is shorter than the others. I'm still going to give them equal weight, but there are fewer problems in it. So I'm going to make it due, on the 2nd, which is after Thanksgiving. Now, if you slip to the 3rd, that's going to be okay, but I'm just trying to give a date, and because I'm going to give one more assignment on Chapter 14. And I'll be giving this later in the week or this weekend, sometime in here, for Chapter 14. I'm going to go ahead and give it so you can get started on it. It will be due to that week of the 9th. Now that's finals week, so I want to, that's why I want to give it this week so that, you have some time to do it over the break. So you'll have both of those assignments will be due after Thanksgiving, so you can work on it during that time. Today I want to do a little bit in the analysis of covariance and then start on regression, which is Chapter 14. So the notes are here for 14. Any questions? Okay, we'll go into our studio, and I guess, I'm in the analysis of covariance. I'm not in the right place down here. Doesn't seem to remember where you are. So we're going to look in Chapter 13. I'm going to go ahead, let me clear that, then I'm going to set the directory just to make sure that we find the files correctly. Okay. So, this particular file is the file for the last part of Chapter 13. In the first part, we looked at fitting a slope, a covariate that has common slope. And here we look at some of the assumptions. So I'm just going to run this, and we've gone through, I think, about all this material except maybe the last part. And I'm going to go ahead and knit this so that we have the output. So these are sections 3 and 4. So what I want to do is just to briefly review how we, in particular that second place where we tested the slopes are equal to each other. I want to go through that just briefly again, although we did look at it last time, and then test if the common slope is equal to 0. So basically, I'll show you how to use the computer to compute these, but if you look at the notation in the book, these sum of squares and cross products, you can use to compute the individual variances. These are the variability about the fitted lines. So in other words, this is the y sub I minus the y hat squared, where the y hats are the predicted values at the x sub i's. And we square those and add them up, and we divide by n sub I minus 2 for the ith group. The reason it's n sub I minus 2 instead of n sub I minus 1 is because we're estimating, we're estimating, it's a regression, we're actually estimating the intercept and the slope, so we're estimating two parameters. We lose 2 degrees of freedom. So we compute these individual variances, and then we could do a Bartlett's test, or in this case I did a Hartley's F max, where I looked at max S sub I squared over the min. And then down below here, I just show you the code for doing this. Basically what happens here is I'm fitting profit tilde, and I'm doing median plus median slash employees. That is the unequal slopes model. In other words, that's actually what these calculations up here correspond to, is fitting individual regression lines and getting the variability about each of those regression lines to get my estimate for each of the S sub I, S1 squared, S2 squared, etc. And so the median plus employees within median, that is how we actually can get the models where we don't have equal slopes, because I'm fitting employees within each month. So that's the unequal slope model. That would be the case up here, where I'm assuming the slopes are not all the same. And then I get the predicted values simply by, if I take the fitted values, the y hats, if I take the model object, profit fit 2, if I take the model object and I predict it, that will give me the y hat sub i's. So that, in other words, will give me these y hat sub i's right here. And then if I get, here I'm getting, profit is the y, so that's y sub ij minus y hat sub ij, and those are the residuals. I call them profit residuals 2, as opposed to just straight residuals from the single slope model. And then I say by data frame, again, what I'm going to do is I'm going to compute the actual variances, and this is the formula. It's actually this formula, and I can't just use the variance, because if I did, it would divide by n sub I minus 1, and I wanted to divide by n sub I minus 2. And so I write a little function, which is this is sum of squares of the profits divided by the n rows minus 2. So in other words, this function is actually the formula for this right here. And so that allows me for each medium, I'm using a by statement. So by median, I'm mapping that function over each of the 3 mediums to get those variances. And then I'm converting them to a vector, and then I'm just naming them. So those are the three. By using the name statement, it gives a name to them. So these are the 3 variances. And if I take the max over the min, that's Hartley's F max. And then if you look it up in the table, which is in the book, I don't believe R has this table. There may be a way to get it, but it's not in the standard packages. So I actually think I looked up the 27.8 in the table in the back of the book. And you can see that you're not even close to being significant, so we fail to reject, and we don't have strong evidence to indicate that this is a problem. Now, when we test for the equality, of the slopes. We basically want to compare the model when we have unequal slopes to the case where we do have equal slopes. And we want to see how much difference it is. So this is a formula, but we actually got it. We actually got that minus 1.5092. That's actually the common slope. You may remember from, it was either section 1 or section 2, we actually computed that common slope. And I'll show you later on where it is. I actually repeat that, and so you can actually find that common slope in some computer output a little bit further down. But I want to get the sum of squares of the deviations about the common regression line, and I'm going to call that G. And I'm going to show you where these are in terms of the output. So, in other words, that sum of squares about the common regression line is G. So that's sort of taking the residuals about each of the regression lines, subtracting them, squaring them, and adding them up. Now the sum of squares about the individual regression lines is what's called H. Now I show you how to compute it, but again, you're probably not going to do it that way. What I want to do is show you a little bit later on where the G and H are in terms of some of the output that I did using R. And then if I take the difference, in other words, I would expect the individual regression lines to fit a little bit better than one single line. One single line is sort of, well, what's the best I can do if I force it to have the same slope? But if I allow them to have different slopes, I potentially can get a better fit. And you certainly won't get anything worse. Therefore, G is always going to be greater than equal to H. It's possible they're about equal. But in general, the variability about the common line will be greater than the variability about the individual lines. Because the individual lines, you get to fit each group separately. So you won't do any worse than fitting a common slope, and you probably will do a little better. Does that make sense? So what we're doing here is we're going to take G minus H, and the difference in degrees of freedom is A minus 1. Because in G, we're only fitting one slope, whereas in the other, in H, we're fitting A slopes. In our case, A is 3. So in the case of H, we're fitting actually 3 regression lines, whereas with G, we're fitting 1. There's 1 common slope, so the difference in our case is 2. But in general, it's A minus 1. So I'm going to take the difference in the sum of squares and divide by A minus 1. And then I'm going to divide that by H, divided by the degrees of freedom from fitting different lines, and that's capital N minus 2A. Is there someone there? So that will give us an F-test for testing the hypothesis that the slopes are not. In other words, if G minus H is small, that means there's not much difference between fitting individual lines versus fitting a common line. So that's how we're going to test it with an F-test. So what we want to do is we're going to look at the unequal slopes model. And I had already fit it above, but I didn't actually save the model. I fit it up here, but I didn't save it. I saved the model object, but so I'm actually I'm going to do it again and call it media fit 2. That's the model object, and I have median plus median / employees. So that's looking at I'm looking at different intercepts for each median, but I'm looking for different slopes, and that slash is called a nesting operator. I'm nesting employees inside of median. Now we've talked about the nesting operator before when we did nested models. Okay, so that's the model we're going to do, and just to show you, here's the model matrix. The intercept is all 1s, and then I have 1s 0 for alpha 1 For alpha 1, I get a 1, 0. For alpha 2, I get a 0, 1. And for alpha 3, I have a minus 1, minus 1, because alpha 3 is equal to minus alpha 1 minus alpha 2. And then notice that I actually get, instead of having 1 column with all the employees listed, I actually have 3 columns. And notice that, again, I'm nesting, so I have the employee information for the first group just in those top 5 observations. For the next group, it's the next 5, and for the third group. So I have three of those variables that I'm going to be fitting. That corresponds to the 3 degrees of freedom for fitting different slopes. So if I do a summary on it, then I get the intercept, and then I get the median 1 and median 2. Remember, a median. The alpha 3 is equal to sort of minus the sum of those. And then I get those are the actual slopes. The minus 1.456, minus 1.48, minus 1.16 are the 3 slopes. You notice they're not that different. The third one drops off a little more quickly. The other 2 are almost the same. Remember, the common slope was a minus 1.51 roughly. So they're not that different. So you would expect that we're probably not going to reject the hypothesis. Now, what I did down here, and I've talked about this before, so I won't go through it again. I'm just showing you how to get this graph. And again, these lines are not parallel. This one is dropping off a little more quickly, as you can see. So now how do I test it, however? How do I test a hypothesis that beta equals 0? Well, the way you test it is actually to test the interaction between the median and employees. We test the interaction because the interaction is, I've discussed this before, you're testing, are they segment-wise parallel? Well, in this case, it means are the lines parallel? And so if I test it with median plus employees plus median colon employees, this last term, median colon employees, is the interaction term. So if I go down here and look at this, I can see that that interaction has 2 degrees of freedom because median has 2. And so I get 2 degrees of freedom, and the f-test, you can see, is 0.22, and the p-value is quite large, so I fail to reject. I have no evidence that there's differences in slopes. Now, where do the G and A, where do all those things come from? Well, let me show you one more model. I have one more model down here. This is the model I fit in the preceding set of notes, where I simply have median plus employees without an interaction term, and that's the common slope model. I don't have a nesting, I don't have an interaction, that is the common slope model. And this was what we got before for the common slope model. And notice that this is the minus 1.5092. That's the common slope right here. Okay. Well, let's go back and look. Remember I talked about the G and the H. And the H was the sum of squares about, the individual regression lines. And that corresponds to these 9 degrees of freedom right here. And that corresponds to 51. More accurately, it's 50.94. So that residual about this interaction model, and I don't know if I printed out this for this other model. I would get the same breakout here with this model. I didn't print out I print out the summary, but I didn't print out the analysis of variance. But if I would have had the same residual. So I have, so the sum of square H is the 50.94 with n 15 minus 2 times 3 or 6, so that's 9 degrees of freedom. So I'm looking at this line right here for H. Well, what about G? G is a common slope model, and it's 2.5. And G minus H is the difference between the common slope model and this. And so where do you first of all get G? What's G? 53.44. Well, let's go down and look at this model. G was the common slope model, and I think I printed it out here. So this is the analysis of variance, and this is the residual, and there's the 53 with 11 degrees of freedom. That is G. That is the sum of squares residual for the common slope model, and the 11 will be n minus a minus 1. In other words, n minus 3, 15 minus 3 minus 1. So if you go back up here, the 53.44, that's G with 11 degrees of freedom. Now the difference, which will be G minus H, it'll be this minus this, which is about 2.5, and the difference of the degrees of freedom is 11 minus 9, or 2. So another, which is a minus 1 also. So this G minus H is 2.5. Now where is that? Well, that's really this right here. But this is rounding off the 2.5 to 2. I don't know if it's really 2.5 or something a little less than that. But that 2 under the interaction is the G minus H with 2 degrees of freedom. And so we actually get an F value. If we divide this by this and this by this, and I take the ratio, I get 0.22. That's my F value, and the P value is 0.81. So there's no indication that I need unequal slopes. And finally, well, again, if I'm testing a hypothesis, okay, let's assume now we say, okay, we have a common slope. Do we need to covariate at all? That would be the next question that we ask. So we sort out the interaction. We say, okay, we fail to reject. We can assume we have a common slope. But having common slope, if the slopes are parallel to the x-axis, in other words, if theta equals 0, then we really don't need to covariate at all. So the next thing is to now, what we did previously back in section 2 or section 1 is we simply tested this hypothesis. But here we're kind of now stepping back. We're saying, okay, test the unequal slopes models first, and then if you fail to reject, now we have the simpler model where we have a common slope model. Now test whether the common slope is even needed. So that's the more correct way to do things. And so, so if I have this common slope model right here, this actually gives me the models, the coefficients. And I showed you in detail how to draw the graph. That's in section 2, I believe, which is in the other set of notes. But again, here is the test. And for testing, in other words, for testing both median and employees, I have a very, very strong rejection. In other words, the p-values are great. So I can't drop out the covariate. I need a covariate. It's just that I can assume that the slopes are common. Now, the final thing to talk about are multiple comparisons. And so I want to talk about the adjusted means. Now, when I say adjusted means, it's adjusted by the model. So we sometimes call them model mean and sometimes least squares means. They all mean the same thing. The adjusted means here are the least squares means or the model means. Same thing. It's the means computed from the model as opposed to just simple means. Now, I showed you they can be quite different. In the one-way analysis of variance, the model means and the sample means are the same, even if the sample sizes are different. But that's almost never the case other than that simple case. So if you look, for example, here, these red right here, here, and here are the sample means, whereas the model means are here, here, and here. They're the means computed at the common overall mean of employees, which is 31. So you can see that the model means, or the adjusted means, or the squares means, whatever you want to call them, but they're not the simple sample means. They're quite different than the simple sample means. So how do you actually compute with formulas the adjusted mean? Well, we can do that fairly easily in this simple case. The adjusted y-bar is simply the unadjusted mean. Now, these are the sample means right here, but they're adjusted minus b, and then that's the deviation of x bar sub I minus x bar. So, if I take, if you look at, if you're looking at a triangle, we can use Pythagorean theorem to sort of figure this out. But what we're doing is, with that formula is we're sliding this mean down along the regression here. You think of it as a right triangle from here to here to here. And the slope is b, or in this case the slope is b sub I. In the common slope model I have the same b, but I don't have the common slope model in this set of notes. They're back in section 2 of it. So I'm really not going to case that the slopes are the same, but the picture is almost the same as this. So what I'm doing is actually sliding this point down along this line, and I'm using Pythagorean's theorem if I look at this right triangle right here. Okay, this says squared plus this squared is equal to that squared, and I can get the slope just using trigonometric functions. So the way we adjust is simply take the regular sample mean and subtract off b times x bar I minus x bar. By the way, x bar I minus, here's x bar I for the ith group, and then this is x bar for the grand. So I'm taking that difference right here and multiplying it times the slope. So that will give us the adjusted means, and I can set a confidence interval on it as the square root of the mean square. It's adjusted mean plus or minus the t-value plus the mean square times 1 over n sub I, and then that's x bar I minus x bar over the sum of squares, the residuals due to the x's. So how can we compute this? Well, it turns out that R has a nice little function that lets you compute these pretty easily. And in fact, not only that, but lets you get lower and upper confidence limits. And that's nice because otherwise it would be hard to compute. So I'm going to create a data frame called new, and I'm going to get just 3 values for the 3 groups. And they'll all be equal to the mean number of employees, which in this case is 31. So if you actually look at the data frame, it will have 2 columns. One will say 1, 2, 3 in Roman numerals, and the other column will be 31, 31, 31. And so I'm going to predict the values from the model for 31, and that will give me 3 different predictions for those 3 observations in nu. So I'm going to predict from the model media fit nu, which is a data frame, and it says SE fit equals true. I want the standard errors, and I want a confidence interval. So this is going to give me a confidence interval on the predicted values and the predicted means in this case. And so in order to do that, I get these are the least squares means, or the model means, or the adjusted means, and then these are the lower and upper confidence limits computed from this. So instead of having to go in and compute all this stuff, R has a function called predict, and it has an option called the standard error dot fit. And if you use it and the plus the interval, you can get the confidence interval on the fitted values. The fitted values here, by the way I define nu, I define a nu as to be the y bar, the x bar. So by defining nu the way I defined it, the new data frame, I'm getting simply the least squares means as the predicted values. So this gives me the confidence limits on them. And here are the standard errors right here. Are there any questions? Now you can also get, we can do multiple comparisons on contrast. That is, we can look at the adjusted mean for y bar I minus the adjusted mean for y bar j, and we can, or I prime, I guess I call it, y bar I and y bar I prime. We can look at those 2 adjusted means and look at the difference, and we can put a confidence interval on it, which is equivalent to testing the hypothesis that there's no difference between each of the possible pairs. So here I'm comparing median 1 adjusted mean to median 2, median 1 to median 3, median 2 to median 3. So I have, in terms of multiple comparisons, this is what I'm doing. Now I think we covered it. When we covered multiple comparisons, I believe that we covered that in the last part of Chapter 10. But we looked at it in that context in the one-way analysis of variance. And when we did that, we simply, how did we do that? Well, we had something called, if you may remember what we did. What is it? Yeah, we had Pairwise Dot T Test. Do you remember that? Pairwise, it might be helpful. So if you look at this is how we did it for the one-way analysis of variance. Now, unfortunately, that's all you can do it for. It only works for the one-way analysis of variance because if you look at Pairwise Dot T Test, X is the response vector, and then, which is profit in our case, and then G is the grouping factor, or factor. In other words, it's assuming that you have a one-way analysis of variance, but we don't. We have a one-way analysis of covariance. And therefore, we're adjusting for the number of employees, and therefore this will not work. Now, there may be a way to finagle it, and at one point I was sort of playing with that. That's actually what this code is at the bottom that's blanked out. This code at the bottom I blanked out. But I was just playing around with, well, could you get Pairwise Dot T Test to work for adjusted means? And I haven't had time to look at that completely, but there may be a way to do it if you pass it the adjusted means. But again, I didn't complete that, so that's just there. It was something I was messing around with, but it's commented out. So let's take a look and see what we can do. Well, here's the formula. And what I'm doing here is I'm using t-apply, employees, median, and mean, and profit. What these are is a sample mean. So in other words, if I look at the first group, 19 and 14, 31 and 10, 43 and 3, if I look at these 2 groups, those are the plotting points for the red points. In other words, those are just the sample means for, they're not the least squares means, they're just the sample means by median for profit employees. So if I wanted to plot those red points, I could use those. But what I need is the least squares mean, and I can get this from media fit and then predicting the new values, and the new values will give me the least squares mean. So these are the least squares mean. So that's not a problem. It's not a problem to do that. And then what I can do is get an outer product. I can get least squares mean, and that I'm getting an outer product with a minus sign. That takes all possible mean differences. Now notice you have 0 on the diagonal, because y bar sub I adjusted minus y bar sub I adjusted is 0. So if I'm taking differences of the same adjusted mean, it's going to always be 0. Now notice I only really need the lower diagonal or the upper diagonal, because the adjusted mean of y bar 1 minus the adjusted mean of y bar 2 is in fact 14.11. But if you reverse the direction you do it, it's simply a minus 1411. So you see that this particular thing up here is just minus what these are down here. Now, in terms of the formula, I get the t value, square root of the mean squared, 2 over n, and then these mean differences. So I can actually write a formula. I can take an outer product of the x bar means with a difference to get all these possible differences. Y bar, x bar sub I minus x bar sub I prime. I could get all those differences using the outer product. And then 2/5 is simply 2 over n. This is the square root of the residual mean squares for y, which is 4.86. Now that's the mean square, so where would that be? Yeah, if I divide 53 by 11, I should get 4.86. That would be the mean square. In other words, this is the common slope model. And so if I take 53 minus 11, divided by 11, I'll get the mean square. So that's where the mean square comes from. So I can get all these pieces. And this sum of squares residual due to x, that's computed someplace in the book. It's simply 650. But you could look at the book and compute that yourself. I'm not sure it's in any of the output I have, but it is in the book, and you could compute it. And so this is the standard error of the differences right here. And then if I take the critical value is the quantile for the t with n minus a minus 1, which in this case is 11 degrees of freedom, times the standard error of the difference. And I ask, is LS fit greater than the critical value? And here are the trues and falses. Okay, so if it's different, it means significant, which means that 1 and 2 is significantly different, and 1 and 3 is significantly different, but actually it means all 3 are significantly different, yeah. So it appears that in terms of what that means is, now this is not quite the right graph, because the graph I'm really talking about is the common slopes, but it's very similar to that. What you're really testing now are these three, that, and that. Are those adjusted means different? And they're all 3 different. In other words, the bottom is 1, the middle one is 2, and the top one is 3. And you can see 1 difference from 2, 1 difference from 3, and 2 difference from 3. They all differ. So in terms of multiple comparisons, the medians are different for each of the 3 groups. I mean, the median effects are significant when I test them individually. So that's how we do this using R. I did want to find out if there is a simpler way to do these multiple comparisons. That's why I was playing around with this code. But as I said, in its straight form, Pairwise Dot T Test only works for the one-way analysis of variance. Okay. So I haven't found how to easily make that adjustment to Pairwise Dot T Test. Basically, you might be able to my idea was to try to do this in terms of the adjusted means, but again, I didn't really check this out to the point whether I know it works or not. But there may be a way to do it. Unfortunately, as I said, if there is a way to do it if you use the theory of general linear models, and that's in fact what JUMP does, which is what I'm going to show you now. Are there any questions at this point? This is all the computer code for doing the one-way analysis of covariance. What I'd like to do now is to go in and I'm going to go into the server. And I'll go down to courses, 512, notes. We're looking at chapter 13, and the media.jump file is what we're looking at. That's the data we've been analyzing. So how do we fit the simplest model? First of all, we're going to go into analyze. We're going to say fit model, and then we have profit, and then I'll do employees and median. So if I do this, we're saying, in our terminology, we're saying profit is modeled as employees plus median. And I'm going to keep this around, so I'm going to run this. So first of all, this is my parameter estimates. That's at minus 1.5092. And these are the median effects and the intercept effect and so forth. And this is the type 2. When I did it, in order to get the type 2, I had to load the library called CAR, C-A-R, and then I had to do ANOVA with a capital A, and that's how I got the type 2 using R. So we can see that both employees and median are highly significant. Now, this is a little bit backwards. Oh, by the way, over here, they have the standard error and the means, and if I wanted to at this point, I could get the least squares means for students T, which is the LSD. And by the way, if I simply do the plot, these are the squares means are the adjusted means, and I could get and see where the differences are. And you can see that all three of these differences are significant, and that's what we showed last time. And this gives the confidence interval on each one of those. I didn't check. Minus 7.26 and minus 0.96. Let's see. One of the things that they may do, 17 and 24, let's see, did it? Need to look at those. They may be taking the, I know that they do, they may be subtracting the mean employees from employees before they do the analysis. I need to sort of check that over, so I'll take a look at that. You can see that I think the F-test, let's see. Yeah, the 304 and 51, you see the two F-tests? And here are the 304 and 51. So the F-tests are exactly the same. If you look at R versus that. There may be a difference in how they compute the standard errors, because if they subtract the grand mean 31 from the mean values, you will make a corresponding adjustment. But I'll take a look at that. Now, that's the common slope means, but suppose we wanted to test, if I take this model and I add the interaction, So now I have employees, median, employees by median. If I add in this interaction term, and I now test, when I go down and look here, this is that, remember that f-test was 0.22, the p-value is 0.8. That's exactly the same results here with 2 degrees of freedom. So this test corresponds exactly what we did before. Now, again, this is the, let me see. That's not what I meant to do. This, yeah. So here I'm doing contrast, assuming that the means are not the same. If you wanted to fit the other model, where I had median employees within median, then I could remove each of these. And I still have profit here. Then I could have median plus, and add this. Let's see. Oh, employees, add it next. And then if I select median and I nest, then this is the way jump represents nesting. I have median and employees, and notice in square bracket as median. That means median employees nested within median. That they use slightly different notation. But that should fit the same model where we have a nested model. If I run this, then I have median nested within median. These are the 3 regression lines. If you actually want to see what the parameter estimates are, they would be here. Now these are the same 3 slopes we had before, but these are different. Now why I know the difference is here due to the fact that instead of using employees, they have employees minus 31. They're centering the data at the grand mean of the x's. So that's going to throw off the intercept term and the coefficient terms for median 1, 2, and 3. And so I know jump is doing it here. You can see that the slopes are identically the same. It's just that the intercept term and the alphas are different, and that's because they've centered the data at 31. So they've subtracted 31 from each employee. So the values for the employees are deviations about the grand mean. So, but this model is the same as what we did, except that they made that adjustment. Now that adjustment doesn't change anything. It doesn't change the predicted value. It doesn't change the p-values. So nothing has really changed, except for the mu hat and the alpha hats. Those are the only things that have changed. But again, the predicted values from the model will be identical. So this is how you do it in jump. I don't know if that will. Oh, well, you can see this plot up here. You can see that the slopes are not equal here. There's this downward trend here, which is slightly greater than these two. So that's the jump version of doing what we did in R. Now, the one thing that would be nice, and I'm not sure where you can do this in R. I'll continue to look. Would be able to do those contrast. To be able to do those contrast without a whole lot of programming. Because right now I had to, if you remember, in order to do the test, I had to do this kind of stuff. It's not a lot, but it would be nice if there were a more direct way of doing it. Are there any questions on this? Okay, well that's how you do it in jump, how you do it in R. So what I'd like to do now is to go into chapter 14 a little bit. How much time do we have? Yeah, so we have a bit of time. We're going to get started in regression, and so I'm going to look at, starting in section 1, I'm going to look at regression, and I'm going to set the working directory here. And just for the sake of reference, so I can talk about it, I'm going to go ahead and nip this so we can look at the output. Now, chapter 14 is the last topic in the book, and this is where we've talked about matrix algebra a little bit, and I'm going to go over some basic stuff today, but I'm also going to give you a handout on some matrix algebra that I developed for another course. And what I want to show you is how to do this matrix algebra in R. So when you take a matrix algebra course, it's a little bit abstract. And we're going to work with real data. And not only that, you will be able to do this in R quite simply. Matrix algebra can get very tedious. So we want to look at a model where you have a single response variable, and before we had alpha plus beta 1 x1, but now we have multiple x's, and let's say k x's. So we have k predictors and one response variable. So you want to predict y is equal to alpha plus beta 1 x1 plus beta 2 x2 and so forth up to beta k x sub k plus some error term. This is what we call, this is a linear model, and it's what we call multiple regression, or it's not simple multiple regression. Simple multiple regression usually means we just have one x, but it is a linear model. Now let us suppose that if you look at this table, that x1 goes along one side and x2 goes down the other side. And let's suppose y goes up here. So my data is scattered around in this three-dimensional space. What we're going to do is fit a plane, a hyperplane, a two-dimensional plane through the data. If you think of points being here, we're trying to fit a plane so that the points, the deviation of each point projected down to that plane, that's the residual. If I take a single point and project down to the plane, the residual is that. If I square them and add it up, that's the sum of squares of residuals for the lack of fit. In other words, the fit's not going to go exactly through all the points because the points aren't going to lie exactly on that plane. How much they vary? Well, in some cases they vary a lot. In other cases they may be pretty tight to the plane. But the probability they'd be exactly on the plane is 0. It just won't happen if you really have random data. The only time it happens if you have some sort of singularity. And that's not the case we're looking at here. I mean, obviously, if y is an exact combination of the x's, then of course, the data is going to fall exactly on that plane. But that only happens in mathematics. It doesn't happen in statistics. So we're going to consider initially the case of where we have two x's, x1 and x2. So we just extended, instead of having one predictor, x1, we're going to have x1 and x2. And so what we want to do is we want to find the fit so that the sum of squares, I wish I could draw better, because I could draw that sort of that plane I was talking about. And but what we want to do is y minus y hat will be that perpendicular. If I take a point y and project down to the plane, the projection onto the plane, if I go straight down vertically, is y hat. Now these are really y sub i's minus y hat sub i's. And then we're going to take that difference, which is the distance from the point to the plane vertically, we're going to square them and add them up, and that's the sum of squares of the residual. But the projection, if I characterized a plane, I can characterize it as A, which is A is where the plane intercepts the y-axis, plus B1 x1 plus B2 x2. Now what I want to do is estimate from the data A, B1, and B2. I want to estimate the two corresponding slopes. So what I want to do is I want to minimize this as I want to minimize that sum of squares for the residual. If I think about moving that plane around, every time I move it a little bit, those residuals change, right? So if I sum and square up those residuals, then I get a different sum of squares of residuals. There's one place where I minimize the sum of squares due to residual. There's one place where I fit this plane and I minimize the sum of squares of residuals. Now, that will be what we call least squares, the least squares place. In other words, least squares means we minimize the sum of squares from each point to the plane, projected vertically down. And now, you might say, well, if I were going to do that, then I could actually take if you know mathematics, I could take the derivative with respect to AB1 and B2 and set that equal to 0, and I have 3 equations and 3 unknowns. In reality, it turns out that you can estimate A separately. So I could simply center the x's about the mean for the x1 and center x2 about the mean for x2, and I could write it in a more simple way without an A, and if I did that, I would have the B1s, but I would have 2 equations and 2 unknowns if I take the derivative with respect to B1 and B2. And those are called the normal equations, which is, you get something here, where the s's, which the S11, S12, S1y, S21, S22, and S2y, those are the coefficients in the equation. And on the left, and on the right-hand side, well, those are the right-hand side elements. I can compute those from the data, and this I show you how to do it. Now, it turns out, of course, you don't really need to do that when you're using R. But these are called the normal equations. And they result from taking the derivative of this. Again, if I center the x1 and x2, then I don't need the A. I can solve, once I get B1 and B2, I can solve A separately. So I have y bar minus B1 x bar 1 minus B2 x bar 2. So I can solve these system of equations, but of course R does it for you. But if you had 2 equations and 2 unknowns, you probably learned in high school through a simple process of elimination how to solve a simple linear equations and 2 unknowns. And you probably even did it for 3 equations and 3 unknowns. Now it starts to get a little more tedious if you get too many equations. You know, if I have 5 equations and 5 unknowns, it starts to get a little tedious, but it's certainly possible to do it. Okay. So that will let us solve for the B1 and B2, and once we have B1 and B2, I can get A as y bar minus B1 times x bar 1 minus B2 x bar 2. So once I know B1 and B2, I can get A. Part of it, you can see that if in fact I center, if I take x bar 1 minus the grand mean of x bar 1, if I do that, then I'm taking deviations, and if I take a cross product of that with the vector 1s for the A or the intercept, then that's going to sum up to 0. And that's why we end up with a set of linear equations, but we really only need to estimate the B1 and B2 because the values for B1 and B2 are orthogonal to the vector 1s if I center the x1 and x2. And that's sort of the justification for doing this, why we can separately do this. But how do we do it in R? Doing it by hand is a little bit tedious, and the book goes through an example where you actually compute this by hand. But how do we do it in R? Well, in R, let's read in blood pressure data. This is BP, is not British Petroleum, it's blood pressure. And so BP.text, this reads in the data, and so here, this is just a very tiny data set where we're measuring the systolic blood pressure, and for each individual we measure their age and their weight. So we have 2 measurements, age and weight, which are the 2 x's, and the individual, we're not really concerned about that. In other words, that's just an identifier, but we don't need to know the specific individuals. So this is x1, x2, and y. The third column is, well, the systolic blood pressure is y. So just to, so I can attach BP, if I read it in, and just for reference, n is the number of rows of BP. The number of predictors, k, is 2. And then what I'm going to do here is center age and weight. So age minus the mean of age is x1, which is centered, and x2 is weight minus the mean of weight. So I've centered both of those. And now remember, that's what JUMP did when I was talking about the analysis of covariance. When they subtracted off the 31 in the analysis of covariance, so 31 is the mean. So that they did center the data. So I'm going to bind in a matrix. C-bind says I'm going to bind x1 and x2 in a matrix, and then systolic blood pressure, I'm going to center the y's here. Now, just to show you a little bit of matrix multiplication, the way we can get S sub xx, which is the cross products of, the x1 minus xy1 squared and summed up is this number right here, and this is the same thing for x2. And then this is a cross product, x1 minus xy1 times the x2 minus xy2, and I take those differences and square them up over all observations. That's 576. So this is the this matrix corresponds to the S11, the S12, the S21, and the S22. If you look here, S11, you see how it's defined. S12 is equal to S21, and then this is his S22, and so forth. So those are the S's right here. Now the way I can get them, I called, if X is a matrix where the first column are the centered means for age and for weight, if I take the transpose of X times X, that's what we call X transpose X. That's what the right-hand side is. And I'm going to show you a little bit more next time when we talk about matrix algebra, how this works. So just kind of accept it today. I'm going to try to clarify this a little bit for next time. So this is X transpose X. So that transpose simply says if you take a matrix and turn it 90 degrees, you interchange rows and columns. That's what we mean by a transpose. We interchange rows and columns. So the transpose of X, and then notice this little sign right here, percent, asterisk, percent. That means matrix multiply. And again, we'll go through that. I'll give you some notes on this for next time, and we'll go through this in a little more detail. But I'm matrix multiplying the transpose of X times X. And what that gives me are these four numbers, S11, S12, S21, and S22. Gives me what I call the right-hand side coefficients. And now I'm going to get the transpose of X times Y, matrix multiply. What that is going to give me is the right-hand side, S1Y and S2Y. And you can see how they're defined here. So in R, it's fairly simple to do. And so here's what we call the right-hand side. Now, basically in terms of matrices, I have the left-hand side in terms of the S's times the coefficients equals the right-hand side. And if you know a little bit about matrix algebra, you know you can take, if I take the inverse of that matrix of the S's and multiply it times the right-hand side, that will give us a solution. Now that's not the way R does it. You can think of it that way. But again, just focus now on the fact that we can do it, and I'll go a little bit more into the matrix algebra next time. I'd like to go, as I said, I'd like to get started, and then I'll sort of backfill some more details of how you do it. The book does show you. It, in fact, shows you how you can compute these by hand, but it's doing a little example. And the reality is, you probably never do this for an example in real life. This only has, 7 observations? So if we've got a small amount of data, yes, you can do it. And we only have 2 X's, 2 predictors. So yeah, we can compute this one by hand. If you look in the book, you'll see how to do it. But you're not going to want to do it for a big problem. And you're not going to want to do it if you have a bunch of x's. But it maybe is instructive to look at because by doing it by hand, you can sort of see what's behind the scenes. So if I look at this, I've got x transpose x, and then solve this s sub xx. Again, this s sub xx is the transpose of x matrix multiplied times x. S sub xy is the transpose of x times y. So these are the coefficients for the left-hand side, and these are the values on the right-hand side of these normal equations right here. So if I multiply each side by the inverse of s sub xx, I'll get my solution for my regression coefficients. And again, I'll show you how that works next time. I can work out a little more detail, but if I multiply the inverse of s sub xx, and the way you can get that is using the solve function. If I say solve of s sub xx, it gives the inverse. If I multiply the inverse times the right-hand side, I will get the regression coefficients. And these are the two regression coefficients. So that's what we did in a nutshell. We got the two regression coefficients. And we sort of calculated it using R, what is done in the book, where it does it by hand. So we've used R basically as a calculator. But again, this is not the way you're going to fit regression models. I just did it for illustrative purposes to reproduce what's in the book. Okay, any questions on section 1? Okay. Now, the way we can get the intercept then, remember, A was equal to y bar minus B1 times the mean minus B2 times the mean. Now, I'm actually using R behind the scenes to compute these. This is B1 and B2. If I multiply, if I multiply y bar, which is the mean of systolic BP, minus B1, which is that element up here, this one, times the mean age, and B2, which is this element right here, times the mean weight, I get A. So this is my model. If you look at these two numbers and you look at A, which is this, that's my model. In other words, y hat is equal to 52.234 plus the intercept, the slope for the x1 is 1.3689, and the slope for x2 is 0.268. So that is my model. That's how, if I plug in any x1 and x2, I get a predicted value. So that's my model. In order to get the predicted values from the raw data, I can simply get y hat, which takes A, which we computed here, times B1, which is computed here, times age is a vector, and then plus B2 times weight. And these are my 7 predicted values. So those are my 7 predicted values. And up here, these are my y sub i's, and these are my y hat sub i's. So what is the variance about the regression plane? So if I take the sum of squares of the residuals, and the degrees of freedom, I've actually estimated k plus 1 parameters. If you think of it as the k betas plus the intercept, I have k plus parameters I've estimated. So I'm going to divide by the degrees of freedom, which is n minus k minus 1. And so I can take the sum of squares for the residual. Let me blow this up. I can take the sum of squares of the residual minus n minus k minus 1, and that's just the total sum of squares corrected minus the sum of squares for a regression, and I can get the variability about the regression line. So if I take SSE is simply the sum of the y minus the y hat squared, so I sum up the y minus y hat, that's the sum of squares about the regression line. And then if I divide that by n minus k minus 1, I get that the variance about the regression line is 74.77. So that is that's all we need. Now, how do I compute? It turns out that you can compute the sum of squares due to regression as beta 1 times the sum of cross products of the x's and y's plus beta 2 times the corresponding for element 2 cross products. That will give us the sum of squares due to regression. And we can do an F test by taking the sum of squares due to regression divided by k, which is 2 in our case, divided by the sum of squares due to error over n minus k minus 1. We get an F test of 22.26, and the corresponding critical value is 6.89, so we're going to reject. Now, what I have done here, if you read the book, I've kind of reproduced what's in the book. That is not the way we're going to do it. We're going to do something more like this using models. We're going to use models to do that, where we do multiple regression models. So it's a good idea to kind of know what's behind it. If you compare what I'm doing here with what's in the book, you'll see that, yeah, we can get all these things. Now, there was a time before we had sophisticated software. If you think about it, in terms of modern software, SAS was about the first one. There was something called BMDP, which was a bunch of 14 routines. But SAS was the first program that came out in the late 60s. And you could actually do all this stuff quite nicely. You had a procedure called ProcGOM. And GOM lets you do regression, analysis of variance, analysis of covariance, all these types of things you could do using ProcGOM. And it was kind of a liberation over what we had to do before, because what we had to do before was sort of like what I just went through, except you had to do it on calculators. Think about that. Back in the 60s. You actually, in other words, you did have some routines. If you knew how to do Fortran programming, you could, in fact, program how to compute these things. But again, it would be much harder than what we just did, because they wouldn't have these built-in matrix things where we can say, okay, we multiply the transpose of x times x. No, that wasn't there. You had to run through a loop or something to do the matrix multiplication. So even though they had Fortran routines to do matrix multiplication, it was still a nuisance to have to do them. So we've come a long ways. In less than 50 years, we have come an awfully long ways in terms of how we do computation. Now, not only that, but it used to be that there were sort of ways, if you did it by calculator, people hunted for very efficient ways of doing it. And there was actually a method called the Abbreviated Doolittle method. It was a row elimination type thing, the kind of thing you might learn in high school, but it was very efficient. And so there were clever algorithms that were worked out that allowed you to do these by hands, but the fact is you still had to do them by hands. Okay, well, we just, we got a little bit into section 2 here, and we'll continue on in section 2 and continue on in regression next time. Okay, remember, I've given you the homework assignment for covariance. And by the end of the week, or sometime this weekend, I'm going to post the final assignment. Now, if you look at 25 points each, and if you look at these assignments, it adds up to 175, not 200. So, as I mentioned, I'm going to go ahead and just give you the last 25 points. So, I'm going to be giving 7 assignments. Any questions? Okay.
Dr. Harner,
yeah.
Assignment for Chapter 12 is due Wednesday.
Yeah.
At midnight? Is that like any time Wednesday?
Yeah.
Like before class or anything?
That's correct.
Okay, thanks.
It could be midnight Wednesday.
All right.
Remember, you to email these to Chin and use the notation to use your, your sort of name, like first initial, last name or something, and indicate the assignment method.